Bismillahirrahmanirrahim. So we will solve a recitation problem for chapter 21. Let's begin. So the first problem is this one. How many electrons are there in a charge of -3 10 to the power -3 Coulomb? Okay. So this is just -3 millicoulomb. So you need to know that 10 to the power -3, of course, is milli. Okay, 10 to the power -6 is micro. Okay, let's say Coulomb, microcoulomb. 10 to the power -9 Coulomb is nanocoulomb. Okay. So you need to know this, okay, because it will come again and again and again. So what do? We know that charge is quantized. So Q here is just n times the charge of an electron, which is -e. N being the number of electrons. So the number of electrons, n, is just Q, which is -3 10 to the power -3, divided by the charge of one electron, which is -1.6 10 to the power -19 Coulomb. And this will give you a number of electron, which is integer and which is 1.9 10 to the power 16. Okay. I can also take absolute value. Of course, absolute value of Q is just number of electron multiplied by absolute value of E, which is the elementary charge. And you will get the same answer. Second question. So the figure 1 shows 5 pairs of identical spheres. Same radius, same area, that are to be touched together, each pair alone. So these two pairs will touch together, these two pairs will touch together, etc., etc. So they are first touched together, then separated. The initial charge on them are indicated. Okay? So initial charge here is +6 E, this -6 E. The initial charge here is 0, it's neutral. Initial charge, and this one is -4, etc., etc. So which of these pairs transferred the maximum magnitude of charge during touching? So I'm asking you to give me which of these pair has a maximum magnitude of charge transfer. Okay, let's solve it. So we have pair number 1, pair number 2, etc., etc. So pair number 1, I know what is Q1, so this is charge number 1, and this is Q2, charge number 2. What is the total charge? The total charge is just Q1 plus Q2, right? And it's equal to what? +2. That's the first thing that I do. So as you know, the total charge is conserved in an isolated system, meaning before touching, Q1 plus Q2 is equal to Q1 plus Q2 after. So the charge before touching, the sum of the charge will be equal to the sum of the charge after. Okay. Good. Now, when they touch, they share. So how much electron which will each of them will have? So here I will have Q1 final, which will be just this divided by 2. So it will be +1. And Q2 final will be what? +1 as well. Okay. It's just the sum divided by 2. Okay. The total charge Q1 plus Q2 before divided by 2. Okay, but still that's not the question. The question is, what is the magnitude of the charge transfer? So magnitude of the charge transfer, so let me write it here, charge transfer will be equal to what? Of course, it will be equal to absolute value of Q1 final minus Q1 initial. Okay? This will be the magnitude of the charge transfer. I look for charge 1. What is the transfer? What was it charged before and what was it charged after? And then I take the difference and I take the absolute value. And of course, this should be equal to Q2 final minus Q2 initial absolute value. Okay, good. Now let's calculate it here. So here I will have basically for 1, I'm going from 6 to 1. So the charge transfer is just 5e. Okay. So for this one also, he will go from minus 4 to 1. So the charge transfer is just plus 5e in magnitude. Now for the second one, what's the total charge before? It's of course minus 4. What is the charge of particle 1 after? It will be total charge divided by 2 because they will share the charge after. So it will be minus 2. For particle 2 also it will be minus 2. Now what will be the charge transfer? I will take 1 for instance. So minus 2 minus 0. So of course it's just plus 2 in absolute value, of course, 2e. Okay. It's the same thing for 2. I will have minus 4 or minus 2 minus minus 4. So you will get 2, etc., etc. So for 3, I'm talking about this one. What's the total charge? It will be minus 12 plus 14. This gives you plus 2. I mean plus 2e. Okay, everywhere I have e. Now, what is the total charge after transfer? For Q1, it will be plus 1e. And for 2 also, it will be plus 1e. Okay, so this 2e here is divided into 2. So plus 1e for Q1 final, plus 1e for Q2 final. Now, what's the charge transfer? Because the charge transfer will be Q1 initial for Q1 final, which is 1e minus 12e. And this gives me how much? 13e. Okay. And the same thing for this gentleman. Okay. Of course, this is equal to the initial final here will be 1e and then minus 14e. Of course, this will give you the same answer, etc., etc. So you get the idea. Okay. We'll do it here. 4 here, you will have 0. Of course, 0, 0. And the maximum charge transfer is, of course, 10e. And for 5, the sum is 10. So each of them will have 5e. And the charge transfer will be what? Who can tell me what should be the charge transfer here? It's just 1. So this one will lose 1. It will become 5. This one will gain 1 and become 5. So the charge transfer is 1. So of course, the 3 has a maximum magnitude of charge transfer. This has the maximum magnitude of charge transfer. Because Q1 final minus Q1 initial in magnitude, which is equal to Q2 final minus Q2 initial in magnitude, is the greatest, and it's equal to 13. Very simple. I took my time because this is very important, and this type of problem will come again and again and again. So how many excess electrons do we have in a negatively charged object with a charge of this minus 35 nanocoulomb? So Q here is minus 35 nano, 10 to the power minus 9 coulomb. Okay. This should be equal to the number of excessive electron multiplied by the elementary charge of an electron, minus E. So n will be just minus 35, 10 to the power minus 9, divided by E, minus E, which is minus 1.6, 10 to the power minus 19. Coulomb will go away. At the end, I will have the number of excessive electrons, which is this number. Okay, this question are the easiest. Now let's solve this problem here. So let's read it carefully. So we have two identical metallic spheres having charge Q1 of 14 microcoulomb and Q2 minus 4 microcoulomb. Okay. So are fixed with a center that are, let's say, 0.3 meters apart. So I have my first metallic sphere, Q1, 14 microcoulomb. Don't forget, microcoulomb is 10 to the power minus 6 coulomb. Of course, Q2 here has a charge of minus 4 microcoulomb. And the distance between these two gentlemen is D, which is 0.3 meters. Put everything in SI units. Now the spheres were connected with a thin conducting wire, then the wire was removed. So I put a thin conducting wire between them. What will happen? They will exchange charges. Okay. So this was before initial. Okay. Now, when I remove the charge, final, this Q1 will have a Q1 final, and I want to calculate it. And this Q2 have a Q2 final, and I want to calculate it. Now the question is, find the magnitude of the electric force, electrostatic force, of course, between these two spheres after I remove the wire. So what is the electrostatic force in magnitude between these two Q1 final and Q2 final when I remove the wire? So the electrostatic force in magnitude will be just F, it will be K, the constant that I know, magnitude of Q1 final in absolute value multiplied by magnitude of Q2 final in absolute value divided by the distance square. The distance square is still 3 meters, 0.3 meters. Okay. Now let's get the Q1 final and the Q2 final. I know the charge is conserved. What was the total charge before? Because here I have an isolated system. So what was the total charge before? Q total was just 14 minus 4. So basically 10 microcoulomb. After, I have the same total charge. Okay, because I connect them by a wire, they will exchange charge. At the end, the total charge will be 10 microcoulomb, but it will be equally distributed between these two identical spheres. Okay, this is very important. It's equally distributed because these two spheres have the same surface. So here I will have what? I will have plus 5 microcoulomb, and here I will have plus 5 microcoulomb. Okay, equal distribution because the spheres are identical. That means that, of course, if I want to calculate the electrostatic force in magnitude, I have to put K, which is 8.99, 10 to the power 9. The unit is Newton meter square divided by Coulomb square, multiplied by Q1 final, which is 5 microcoulomb, which is 10 to the power minus 6 coulomb. Don't forget this. Multiply by 5, 10 to the power minus 6 microcoulomb, coulomb, sorry, for that. Divided by the distance square, which is 0.3 meters square. Okay, coulomb goes away, meter square goes away, and I get my number, which is just 2.5. So 2.5 Newton. Okay. So the electrostatic force between these two equally charged spheres that are identical is just 2.5 Newton. I can ask you also, what was the electrostatic force before I connect them with a wire? You can calculate it easy. Okay. The electrostatic force before will be just F, K, Q1 initial, okay, which is 14 microcoulomb, 10 to the power minus 6 coulomb. Q2 initial, which is just, I'm looking in magnitude, right? So taking absolute value, or 10 to the power minus 6 Coulomb divided by distance squared. And you can calculate it. Now, next question. Let me erase this. Same type of question. Two small metallic spheres, A and B, are positively charged, but B has twice the charge of A. So they are touched and then separated. After separation by 10 centimeters, the electrostatic force between them has a magnitude of 0.45 Newton. What was the initial charge on A? So here we have sphere A and sphere B. So sphere A has an initial charge of QA and sphere B has an initial charge of 2 times QA, and both of them are positively charged, so plus, plus. So they are touched. So this was before, right? Initial. What is the total charge? The total charge is just Q total, just 3 QA, okay? Which is just QA plus QB. Now, when they are touched and separated, what happens? They exchange charge. Since they have the same, they are identical, so same surface area. So final, when they are touched and separated, so A will have a QA final, and B will have a QB final. But QB final and QA final, the total charge will be the same as before, 3 QA. So basically QA final will be just 3 QA initial divided by 2. And here you have 3 QA initial divided by 2. So the total charge is conserved, okay? I have conservation of charge in an isolated system. So total charge before is equal to total charge after. Now, I told you that the electrostatic force between them, F, between A and B in magnitude, after, is just K, QA final, multiplied by QB final, divided by the distance squared. And this electrostatic force between them in magnitude is just 0.45 Newton. So now the question is, what was the initial charge on A? Easy. So I just say that 0.45 Newton is equal to K. I know K. What is K? 8.99 10 to the power 9. QA final is just 3 halves of QA initial. This is my question. This is what I want. And QB final is the same. So I have to take it 2 times. So this squared divided by D square, and the difference, the separation is 10 centimeters. Of course, we put it in meters, okay? Because this is an SI unit. Everything here should be in SI unit. So 0.1 meters square. And this should give me 0.45 Newton. So I know everything here. My only unknown is QA final. So we will have that QA initial. QA square will be just 0.45 times 0.1 square divided by 8.99 10 to the power 9. Now don't forget this 3 half square. So basically you multiply by 4 divided by 9. I want QA. You take the square root. If you do that, you will get that QA initial charge on A was just 0.47 10 to the power minus 6 Coulomb. It will give it to you in SI unit. Okay. Now this is just microcoulomb. So you have this answer 0.47 microcoulomb. Okay. So this type of question for sure will come in the exam. So you know how to solve it. Conservation of charge, total charge before is equal to total charge after in an isolated system. And since the two spheres are identical, after they touch and then separated, I will have equal distribution of charge. Okay. Okay. QA final is equal to QB final, okay, which was just the total charge divided by 2. Good. Let's go to the next problem now. So here we have 3-point charge that are arranged in the figure 6 below. What is the magnitude of the net electrostatic force on the minus 10 microcoulomb charge? Okay. Again, you know micro, 10 to the power minus 6. Okay. Milli, of course, 10 to the power minus 3. Nanocoulomb, 10 to the power minus 9. Pico, 10 to the power minus 12. Okay, so most of these are in your formula sheet, by the way. Okay, so you put everything in SI units, don't forget, because my K, which is 8.99 10 to the power 9, is in SI unit, Newton Coulomb square divided by meter square. So in my calculation, I put everything in SI units. Okay, so these are in your formula sheet. Okay, kilo 10 to the power 3. Don't make the same mistake as you did in LF, you know, the heat of transformation. Kilojoule, don't forget the 10 to the power plus 3. Milli 10 to the power minus 3. Micro 10 to the power minus 6. Nano 10 to the power minus 9. And of course, pico 10 to the power minus 12. All of them are in your formula sheet. Now let's solve our problem here. So I have free charge, point charge. So this first charge, let me call it Q1, is positive 5 microcoulomb. And here I have Q2, which is equal to minus 5 microcoulomb. And here I have Q3. Let me call it Q3 here. Okay. So Q3 is equal to minus 10. Now the question is, what is the net magnitude? What is the magnitude of the net electrostatic force acting on Q3, which is minus 10? So Q3 is my minus 10 microcoulomb. So first, I know that net force, electrostatic force on free, is equal to principle of superposition, force on free by 1 plus force on free by 2. So this is my net force on free. So now what is force on free by 1? So 1 is positive, this one is negative. So what's the direction of the force? Of course, it's an attractive force. So this is force on 3 by 1. I can know what's the magnitude and I can know what's the direction. Now, what about this one? Force on 3 by 2. Both are negative, so it's a repulsive force, right? So it's moving in this direction. I mean, the force is in this direction. This is force on 3 by 2. Okay. This is an attractive force. This is a repulsive force. Now, we know the magnitude of the force and also we know the directions. So let's just calculate the net force. So first, I will choose carefully my axis. So this is my x-axis here, and this is my y-axis. Okay. And Q3 is at the origin 0 here. Now, what the magnitude of F13 in magnitude? I'm talking in magnitude. So magnitude will be K, absolute value of Q1, absolute value of Q3, divided by the distance square. And the distance here is given 2 centimeters. So let me put 0.02 meters square. So let me calculate the magnitude. So how much do you get for the magnitude? 8.99 10 to the power 9 times Q1. Q1 is 5 microcoulomb, so don't forget 10 to the power minus 6 coulomb. Q3 is just 10, but I take minus 10, so I take the absolute value, 10 to the power minus 6 Coulomb divided by the distance square, which is 0.02 square. So when you calculate this, you get 1,125 Newton. Okay. This is the magnitude of your force, F on 3 by 1. Okay, and then F on 3 by 1, which has the same magnitude as F on 1 by 3. But I don't want this one. I want on 3 by 1. Okay, but I'm looking at the net force on 3. So this is what I have. Now let's calculate the second one, F on 3 by 2. You see, it will give you the same. K, absolute value of Q3 multiplied by absolute value of Q2 divided by the distance square, which is this distance square, which is the same, 0.02. I put it in meters, okay, square. And you see that it will give you exactly the same answer, okay, because, you know, everything is the same. 8.99 10 to the power 9. Q3 is 10 to the power minus 6. We put it in Coulomb. Q1 is absolute value, of course, is 5 to the power minus 6 divided by 0.02. It gives you exactly the same answer, which is 1,125 Newton. Now, we know the magnitude. Now let's get the direction, okay? Because I want to project. So first, the first direction I want is this direction. What is this angle here? Okay. And then what is this angle here? Of course, these two angles will be the same, but we will see it just in a second. So how to get these angles? I will use the data of the problem. So here I have 3 centimeters. So that means here I have 1.5 centimeters. So this is what? 2 centimeters. So I can get what is this angle here. Okay. So what is this angle here? Let me call it theta. Sine theta will give you this 1.5 divided by the hypotenuse, which is 2. Okay. So that will give you what? An angle of, so theta is just sine inverse of half divided by 2. So that gives you an angle of what? So use your calculator. So we get a sine theta, basically at an angle theta, which is sine inverse of half 3 divided by 2. Okay. So this gives you 48.6 degrees. So this angle theta here, its sine is just this opposite side divided by hypotenuse. So half 3 divided by 2. So the angle is 48.6 degrees. So that means F31 has 2 components along X, just magnitude. Now, along X here, it's negative, right? So you'll have minus, and then you'll have cosine 48.6 degrees. Along Y, it's positive. You'll have plus F31 sine 48 plus 6 degrees. Okay. F32 on 3 by 2. This is this force here. Now here, look, this angle theta is the same angle here. Why? Because of symmetry. Okay, this theta here is the same as this theta here. Okay, and it's equal to this angle. So this angle here is an angle theta. So I will have F32 cosine 48.6 degrees, and along Y I will have F32 sine 48.6 degrees. Okay. So the net force on 3. So these two are equal, okay? Remember, F13, F31 is equal to F32, okay? So this net force along X is 0. You can see it. This component here and this component will give you 0. Now along Y, you will have 2 times, because F31 is equal to F32. So 3 times 1,125 Newton sine 48.6 degrees. Okay. So this will give you 0, of course, along X. The net force is 0 along X, and along Y, you will have what? 1.69 10 to the power 3 Newton. Okay. Which is basically 2 times 1.125 multiplied by sine theta. But remember, sine theta is 1.5 divided by 2. So it just gives you, 1.125 times 1/2. And this gives you this answer A, of course. So we are just applying what we learned in vectors. But here we are applying it to electrostatic force. Okay, we know the magnitude and we know the direction. And then we get the net force on 3. We decompose component by component, and I can solve any problem with that. Next question. Let's solve this problem now. So we have 3-point charges that are fixed in the XY plane, as shown in the figure below. We have this charge here, this charge, and this charge. So the question is, what is the magnitude of the net electrostatic force acting on the +4 microcoulomb charge here? Okay, so just for the sake of calling these charge, so this charge has a charge of -8 microcoulomb. So I will call it 8, for instance. Okay. This charge has a charge 4, I will call it charge number 4. This charge has charge 6, I will call it charge 6. Okay. So I'm asking you, what is the net electrostatic force on 4? So what is F for net in magnitude? We know that, of course, F for net is equal to F4 on 4 by 6 plus F on 4 by 8. So how is F on 4 by 6? Both of them are positive, so it's a repulsive force. It's towards the left here in the negative X direction. This is F on 4 by 6. Now what about F on 4 by 8? Positive, negative, so it's an attractive force. It's going towards 8. So this is F on 4 by 8. So I know the magnitude of each of them. What is the magnitude of 4? 6. It will be K, absolute value of Q4, multiplied by absolute value of Q6, divided by the distance square, which is 4 meters squared, 4 squared. I can calculate it. It would be K, and I know K, and I know absolute value of Q4, so I have 4, 10 to the power minus 6, okay? And then I have Q6, which is 6, 10 to the power minus 6, and I know the distance square, which is 4 square. So I can calculate the magnitude. What about, what is the magnitude of F for 8? F on 4 by 8, K, absolute value of Q4, which is 4, 10 to the power minus 6, absolute value of Q8, which is 8, 10 to the power minus 6, divided by the distance square. And what is the distance square? Is 4 square. So here I made a mistake because I'm looking at this distance, of course. So this distance is 3 square. So be careful here. So it's 3 square, right? So here it's 3 square. Okay? For the 4, F46. F48, this is 4 square. Okay, this is this distance. The first distance was this distance, and it's equal to 3 meters. So 3, okay. So I know this one. Now the net force, here it's easy. Yeah, because basically I know that these two are having 90 degrees between them. So the net force will be just somewhere here. So the net force on 4, F4 net will be just square root of F4 6 square plus F4 8 square. Okay. And we calculate the net force because the two forces are perpendicular to each other. Very simple. Good. Now let's go to the second question. So this is what we did here. Okay. This is F4 6, and I calculate the magnitude. It's to the left. And this is F4 8. I calculate the magnitude. It's downward, and the net force is this. Clear? Good. Now let's go now to the second question. The second question is, what is the magnitude of the net electrostatic force on the charge -8? So I want here now. Okay. As I said, this is my 4, this is 6, and this is 8. I want to calculate the net electrostatic force on this charge. So F net 8 will be equal to F on 8 by 4 plus F on 8 by 6. Now F on 8 by 4, how it will look like. Okay, on 8 by 4, so these two are attractive toward each other. So F and 8 by 4 is this. Okay, and it will have the same magnitude as F on 4 by 8 that I calculated in the previous problem, in the previous question. Okay. So it will be upward. It's an attractive force. So 8 is attracted towards +4. So I know that component along X is 0 and along Y is positive, and it will be equal to 8 for F8 4, which is what I calculated before, which is 0.018 Newton, right? Yes. Now, F8 6, how it will look like, I can know easily the magnitude, right? What is the magnitude of F8 6? It's K, absolute value of Q8, which is 8 10 to the power -6. Absolute value of this one, which is 6 10 to the power -6, divided by the distance square. Now, what's the distance between 8 and 6? Pythagorean theorem. So this is 4, this is 3, the diagonal is what? 5. So we'll have 5 squared. The distance 8 6 is the square root of 4 squared plus 3 squared, which is 5. Okay, so I know the magnitude. Now, what about the direction? Well, I can easily know the direction. Okay, so if this is, so of course, this force is an attractive force, right? Because this is positive, this is negative. So let me draw it. So this will be my F8 due to 6. F on 8 due to 6. Okay, it's going along the diagonal. And I know the magnitude is this. Now, what's the direction? Of course, if I call this angle theta, cosine theta will be what? 3 divided by 5. And sine theta will be 4 divided by 5. Okay. If I call this angle theta, of course, right? Good. So that means here, I know the magnitude, F8 6, that I can calculate from here. Now I will take cosine theta to get the x-axis. So cosine theta will give you what? 3 divided by 5, and sine theta, 8 6, is just 4 divided by 5. Okay. Good. So now I know my net force. So net force on 8 So it has two components, 0 plus this, so 0 plus 3 divided by 5, F86. And then along Y, we will have 0.018 plus 4/5 of F86. Okay, so I know perfectly what is my net force acting on 8, and I know the two components. Okay, so the magnitude of F net 8 will be the square root of 3 divided by 5 F86 square plus 0.018 plus 4 divided by 5 F86 square. So I know what's the magnitude, and the magnitude will give me exactly this number, 0.03 Newton. Okay. So you get the component of the net force on 8, and then you apply this, what you know. Okay. The magnitude is just square root of, this is F8 net x, this is F8 net y. It will be square root of F8 net x square plus F8 net y square. Okay. And that will give you 0.033 Newton. There is another way to calculate it, okay? And that's what I showed you in this solution. This solution, okay? You can use this. Yeah. So students, you took Physics 101. This can be demonstrated quite easily. Okay? So now let's solve this problem here. Read the problem carefully. So the question reads, on an x-axis, a point charge of 10 microcoulomb, so plus 10, is fixed at 1.06 meters. And another point charge of minus 20 microcoulomb is fixed at minus 10, or minus 1 meter. What should be the position of a third point charge on the x-axis such that the third point charge is in equilibrium? So number one, let me draw my x-axis. This is my x-axis. This is my origin. Now the first point charge is positive and it's located here at 1.06 meters. And I have Q1, which is just plus 10 microcoulomb. And my second charge is located at minus 1. So let's say this is minus 1 meters. And Q2 is minus 20. Okay. So you see this charge have different sign, and also they have different magnitude. Okay. So whether my third charge is positive or negative, it doesn't really matter, because one of these Q1 will attract it and Q2 will repel it, or either Q2 will attract it and Q1 will repel it. So you will have, whatever my third charge is, positive or negative, you will have two competing forces, one attractive force and one repulsive force. So there is a possibility for that third charge to be in equilibrium. And when I have an equilibrium on my third charge, so free of charge Q3 at equilibrium, it means that F net on 3 is 0, meaning F on 3 by 1 vector plus F on 3 by 2 vector is equal to 0. Okay. Meaning equilibrium for particle number 3, it just means that the magnitude of F on 3 by 1, by this charge 1, in magnitude is equal to F on 3 by 2. Okay. These two electrostatic force will cancel each other. So same in magnitude, but opposite in direction. So what is F on free by 1. Of course, f on free by 1 will be just k, absolute value of q free multiplied by absolute value of q1 divided by the distance. So the distance, I need a distance here between 3 and 1. So let me write it down here, distance 3 and 1 square. And what is the magnitude of F32? Of course, it will be K, absolute value of Q3, absolute value of Q2 divided by the distance between 3 and 2 square. You see, K will cancel. Absolute value of Q3 will cancel. Okay? Whether Q3 is positive or negative, it doesn't matter, because there will be always a position at which I will have a repulsive and an attractive force, because these Q1 and Q2 have different signs. So basically, I have a possibility to be at equilibrium at that distance. Okay, now, what is D1 free? The distance between 1 and 3. So if my particle is at position X, let's say X, anyway, in my x-axis, what's the distance between Q1 and 3? So particle 3 is here, Q3 is here. So this distance here will be just the absolute value of x minus 1.06. Okay. And the distance between 3 and 2 will be just the absolute value, sorry, not square, of course, between x minus now minus 1. Okay. So it will be just x plus 1. Okay. So here I'm just using the fact that basically D31 is just x3, which is x minus x1. And D32 is just x, which is x3 minus x2. Okay. I'm looking for distances. So this will lead me to what? Q1, absolute value, divided by x minus x1, which is 1.06 square. This is equal to absolute value of Q2 divided by x minus x. Q2 divided by x minus x2. What is x2? X2 is minus 1. So minus 1 plus 1 square. Okay. Q1, you remember, absolute value is 10 microcoulomb. Okay, and here you will have what? 20 microcoulomb. Okay. 10 to the power minus 6. 10 to the power minus 6. Anyway, so what does it mean? It means that x plus 1 square divided by x minus 1.06 square. This will be equal to Q2 divided by Q1. And this will just give you 2. Okay, the microcoulomb will cancel. You have 20 divided by 10, which is 2. So let's solve it. We will have x plus 1 square. Well, let me take the middle of the square. If I take absolute value of force, this will be square root of 2. So I'll have x plus 1, the square root of 2, and x minus 1.6. So that means basically x square root of 2 minus 1. This will be equal to what? 1 plus put this sentiment over there. So I will have plus square root of 2 times 1.06. X is equal to. So this will give me x is equal to 6.03 meters. Okay. Clear? Okay, good. Let me go to the next problem. So this problem also is almost the same. Let's just solve it. Okay, so you need to know how to solve this type of problems. Two fixed particles of charge Q1 is 1 10 to the power minus 6 Coulomb and Q2 minus 9 10 to the power minus 6 Coulomb are 10 centimeters apart. So how far from charge Q should a third charge be located so that the net electrostatic force on it is 0? There is no net electrostatic force acting on it. So first I will draw my x-axis. So let me choose, for instance, charge Q1 be at my 0. So Q1 is here. And I know the charge Q1, 1 microcoulomb. And Q2, let's say that Q2 is here, minus 9 microcoulomb, and it's at 10 centimeters, so 0.1 meter away from Q1. So if I want a third charge, so let's say Q3 on this axis, such that there is no net electrostatic force on it. So let me call it Q3, can be positive or negative. And then I say, for instance, there is no net electrostatic force on it. So that means F on 3 net is 0. That means F on 3 by 1 plus F on 3 by 2 is equal to 0. That means that in magnitude, of course, F31 is equal to F32. Okay. Now, what is F31? F31 will be just K, absolute value of FQ3 multiplied by absolute value of Q1 divided by the distance square. So let's say that particle is at a distance x. Okay. So what will be the distance? 31. Okay. Square. I'll just call it x. So distance 31 will be x3 that I have called x minus x1. But x1 is 0 here because I'm at 0. So basically x. Okay. That means absolute value, of course, because we are looking for a distance. And here you will have K, Q3, Q2 divided by D32 square. What is D32? Will be absolute value of course, x3, which I call x, minus x2, and I know what is x2, right? So it will be just x minus x2, which is 0.1. So bottom line here, I can simplify by K, and I can simplify by Q3. So I'll end up with Q1 divided by x square should be equal to Q2 divided by x minus 0.1 square. So let's solve this. So I will have what? X minus 0.1 square divided by x square is equal to Q2 divided by Q1, which is equal to 9, by the way. Okay. So that means I have x minus 0.1 divided by x. This will be equal to plus or minus 3. Okay. So what does it mean? I just have x minus 0.1, which is equal to plus or minus 3x. So that means x minus or plus 3x, this is equal to 0.1. So that means x minus or plus. So basically x is equal to 0.1. Okay, this gives me x, which is 0.1 divided by minus 2, or x is equal to 0.1 divided by 4. So this will give me x is equal to minus half meter, or x is equal to plus 0. Let's say, okay, 0.05, sorry, here. So 0.05 meters or 0.025 meters. Okay. So either x is at minus 0.05 meters, or x is at plus 0.025 meters. So why do I have two solutions? Well, we know that Q1 is positive and Q2 is negative. Okay, let's consider this one. So I'm here at minus 0.05 meters. Okay, so if this guy is, if Q3 is positive, what will happen? Of course, this one will repel it, but this one will attract it. Okay. And I can be in equilibrium. If Q3 is negative, that means here, Q3 will be negative, but this one will attract it. It will attract it with a force, right? So what I want to tell you is we have both solutions and both of them are good. Okay. So here we find two solutions. Okay. Either x is equal to minus 0.05 meters. That means that my fluid particle Q3 is here, whether it's positive or negative. Q3 is somewhere here, okay? So this is my 0, so I'm here. So how far? Of course, I'll take the absolute value, okay? Because the question is how far? How far? It will just give you absolute value, which is 0.05 meters. Now I'm talking about this one, okay? So this distance here, okay? So this is a solution. Or I am at plus 0.025, meaning I'm somewhere here, okay? 0.025. This also is a solution. Okay? This is coming from the fact that, square root of 9 is either plus or minus 3. So in this type of problem, there is always two solutions. But in general, I focus with, the square root of 9, which is 3. So if I had 3 here, simple, the question will be, the answer will be 0.5. But there is another solution. Now let's go to the next problem. So this problem, we already solved it. Okay, we already solved it. But let's do it quickly. We have Q, which is minus 140 microcoulomb. You have small q, which is 66 microcoulomb. So here I have minus 140, and here I have minus 140 microcoulomb, and here I will have plus 66 microcoulomb. Okay, so this is at 0, 4, 0. This is my origin. So 0, 4, and the second one is at 0, minus 4. And Q is at 3, 0. Okay? This is my x-axis, and this is my y-axis. Now, what is the net force on the smaller charge Q? That's the net force here. Of course, this is negative, this is positive, so there is an attractive force. So this will be my first force, F on Q. Let me call this position 1 by 1. And this is also an attractive force, same magnitude, opposite direction, of course. I mean, same magnitude, but in the direction of this. So it will be like this. So force on small q by 2. So this I call it 2. So you will see that basically these two forces have the same magnitude. Okay? And the magnitude of F Q on 1 is equal to F magnitude of F on Q by 2, just K Q divided by the distance square, and the distance square will be the hypotenuse here. So 25, basically 5 square. So same magnitude. And again, this angle here will be this angle here. Okay. And you can get what is the sine and what's the cosine of this angle. Basically, the net force, of course, will be along negative x, because along y, they will cancel each other. Net force will be 0 along y, and along x, it will be basically minus 2 times F Q1 in absolute value multiplied by cosine theta. So let's say if I call this angle theta, we know that cosine theta is just 3 divided by 4. Okay, so we already solved this problem already. So that's what we did here. Okay, it's here, it's here. So it's already here. You'll find 2, so it will be minus 4 Newton on the negative x direction. So this problem also, you need to solve it. We can solve it. So let's read it. So we have a particle of charge this is positive, which is at this position. And then another particle of charge Q. I cannot give you the sign or the magnitude of the charge Q, so that would be the question. Fixed at this position here. So if the net electrostatic force on a third particle of charges located at this is 0, what should be Q? Okay. So again, let's say this is charge 1, okay, at position x1, and then I have charge 2 that I don't know. Basically, charge 2 is what I call Q. But at position x2, and x2 is just this one. Now, where should be my third charge, my third particle of this charge? And I give you where it is, such that, I mean, I know where it is, but I'm asking you what should be this Q2, such that the net charge on 3 is 0. Very simple, okay? Net force on charge 3 should be 0. So the magnitude on 3 of the force on 3 by 1 is equal to the magnitude on 3 by 2. Okay, these forces have the same magnitude in opposite direction. And you apply the same thing as we said before. The K go away, the Q3 goes away, and then I will have just the charge of Q1 divided by the distance between 1 and 3 squared. Okay, is equal to the charge of Q2 divided by the distance between 3 and 2 squared. So this is what I get. X3. So by the way, what is X3? I know X3. X3 is just this, 6.23 centimeters minus X1. I know what is X1, 1.43 centimeters. You can put them in meters if you want, okay? But I know that they will cancel each other. So here I will have Q2, which is a Q that I want, divided by the distance between 2 and 3. So what is X3? I know X3. X3 is 6.23 centimeters. Now, what is X2? I know X2, right? X2 is given. X2 is just this, 3.67 centimeters. So if I leave them here in centimeters, here I should leave them in centimeters. If I put one in meter, I should put the other one in meter. They will simplify anyway. So I know this one, Q1, just 463. So Q in absolute value will be what? 623 minus 367 divided by, okay, don't forget the square, but here, don't forget the square. Okay, so square divided by 623 minus 143 square. Now times Q1, which is 468. So you calculate it and you will find it. But when you find it, you find it positive, absolute value, of course. But it should be negative, right? Because this one is positive, this one should be negative, such that the net force on Q3 is 0. Okay. So if Q1 is positive, Q2 should be negative. Okay. So here we get the absolute value. You do it and you get it right. And then you take the negative value. Because if Q1 is positive, Q2 should be negative, such that the net force on this Q3 is 0. So this type of problem will come again and again and again. Okay, so now, I want you to solve this problem as well. It's not difficult, okay? You go through it, okay? The solution is given, straightforward, okay? And then I want you to solve this problem. And this problem. And you solve all the rest of the problems, okay? So they are not difficult, but you need to focus. Let me solve this problem just for you to be convinced that it's easy. So we have two neutral metal spheres that are separated by 20 centimeters, 0.2 meters. How many electrons must be transferred from one sphere to the other sphere so that the electric attraction is 10 to the power minus 10 Newton? So at the beginning, they were what? Neutral. So the force, electrostatic force, is 0. Okay. Now I transfer electron, from one to the other, and I'm creating an imbalance. Now the force, new electrostatic force, is just in magnitude 10 to the power minus 10 Newton. And this is K. Now the new charge of the sphere, let me call it QA, UB divided by the distance, which is 0.2 square. Okay. Now, how many electrons have been transferred? That's the question. In another word, basically, what is QA and what is QB? So we know that at the beginning, we have two spheres, A and B, and QA is 0, and QB is 0, right? And they are separated by 0.2 meters. Now at the end, I have QA and QB. But because I have conservation of charge, of course, if QA is minus Q, QB will be plus Q, such that the total charge is 0. The total charge at the beginning was 0, Q total. 0 plus 0 was 0. So here also, Q total is 0. So that means if A is minus Q, B should be plus Q, such that the total is 0. So I will plug them here. So I will have this. This is just K. QA in magnitude is equal to QB in magnitude. So Q squared divided by 0.2 square. So I know everything. So my only unknown is Q. What is now the new charge Q? So of course, we can calculate it. It will be square root of 0.2 square times 10 to the power minus 10 divided by K, which is 9, 10 to the power 9. Don't forget to put everything in SI units, so you'll get Q in Coulomb. Okay, so once I get Q in Coulomb, I say that, you know, the charge is quantized. So is equal to N multiplied by E, E being the elementary charge. So I will know that basically N will be just the Q that I find divided by E. And that will give me how many electrons have been transferred from one sphere to another sphere. Okay. Again, after I transfer, QA is minus Q, QB is plus Q. Is it clear? Good. So this is what we did here exactly. Okay, this is what we did, just without the explanation. But the drawing that I showed you before is explaining this. Okay. This is the F that I already know, 10 to the power minus 10. This is K, this is a distance square, 0.2 square. I'm saying this bit goes QA is equal to absolute value of QB, which is Q. Okay, so from here I get Q, and then I divide by, so I get it here, 2.1 10 to the power minus 11 Coulomb. And then I divide by the charge, elementary charge, and I get the number of electrons that has been transferred. Next question, same thing. Determine the magnitude and the direction of an electric force. Okay. So please do it, okay? Vectors. So do it, you will get used to it, and then, of course, it's very easy at the end. We just are translating what we studied in Physics 101, we apply it to an electrostatic force. Okay. Net force here will be equal to what? F, I'm looking for net force on 2, right? So it will be force on 2 by 1 plus force on 2 by 3. Okay, so force on 2 by 1, I can get the magnitude. And then I can get the angle as well. Okay, I can get the component. Here I will have cosine theta, here I'll have sine theta. And then I'll check. Okay, which one is negative, which one is positive. So here both of them will be negative. Okay. And then I'll calculate F on 2 by 3, which is this one. Right? So I'll calculate the magnitude F on 2 by 3, easy. F on 2 by 3. So the component along X will be cosine 60 degree. So this angle will be 60 degree because this is an equilateral angle. So 60, 60, 60. So this angle here is 60 degree, of course. And of course, this theta is 60 degree. This angle also is 60 degree. So here it is positive along X and negative along Y, minus 2 sine 60 degrees, okay? And then you calculate the net force along X and along Y. And you see that the net force along X is 0. The net force along Y is the sum of these two gentlemen here. So effectively, my net force will be along negative Y, because this component along X, they cancel each other, okay? The same type of thing will come again and again and again and again, okay? So practice, practice, practice. That's all what I can say. Okay. Well, this is also straightforward. Please solve it. You solve the rest and you are ready for any problem from chapter 21. So I will post also the recitation problem for chapter 22. Enjoy them, solve, and you are ready for the exam, inshallah. Okay, let me solve this problem because it's interesting. Let me solve it and you will see. So the figure shows 3 identical conducting spheres. All these spheres are identical, A, B, and W. Same radius, so same surface. So at the beginning, they are separated from one another. So sphere W with an initial charge of 0. So this sphere W, its initial charge, let me write it, QW is 0. It's neutral at the beginning. So it's touched to sphere A, then separated. So let's assume that sphere A has a charge of Q. So if they touch, I have conservation of charge, right? Total charge before between A and W is just Q, okay? This is 0 plus Q, so it will give you Q. So when they touch, QW will be charged, and the new QW will be just half Q. And the new QA will be half Q as well, okay? Because I have 0 and Q, after they touch between A and W, each of them will be half Q. Now that's what I did here. So they are touched, W and A are touching each other, then separated, and each of them have half Q. Then W, sphere W, is touched to sphere B, and the initial QB is minus 14. Do you agree with me? It's given here with an initial charge of minus 14. So they touch each other and then they are separated, okay? Now the final charge for W is plus 14. So after these two touch each other, so this one, QB is minus 14, QW is Q divided by 2. After they touch each other, the new QW is plus 14. So who can tell me what is the new QB? The new QB also will be plus 14, okay? Because they touch each other, they exchange, and they end up with the same final charge. So if QW is plus 14E, QB, the new QB will be plus 14E. Now let me apply what? And the question is, what's the initial charge of sphere A? What is Q? Let me apply conservation of charge between W and QB. So before, what do I have? Of course, the total charge between W and B was minus 14 plus Q divided by 2. And this should be equal to the total charge between W and B after, which is 14 plus 14, so which gives me 28. Okay. So again, I know that if QW is 14, QB will be 14 because they exchange, it's the same surface, identical sphere. So they exchange charge and then divided by 2. So I end up with minus 14 plus Q divided by 2 is plus 28. That means Q divided by 2 is just 28 plus 14, which is 42. That means Q is just 42 times 2, which is 84. So Q is 84E, which is QA. Okay, so initially my A was 84. And you can check 84 and 0, so I had 84. Then this gentleman here has what? W will have 84 divided by 2, so 42. Okay, so now the total charge between W and B is 28, right? Okay, so if this is 14, this should be 14. That's what I wanted to show. Okay, so here it's said in a different way, but all the ways lead to Makkah and you get the right answer. So solve the rest of the problem, okay? That's the only way you will improve, by solving and solving and solving, and you will get better and better and better. And inshallah, in the final exam and in the midterm exam and in the quizzes, you will get full mark. Okay, this is the same problem. Okay. So thank you very much and see you next time. Assalamu alaikum.